Let's continue with JFET, and today what we are going to do is we are going to look into the construction and working of a junction field effect transistor. Okay. So the other day I did tell you about the construction part. Okay, we already know how it is exactly constructed. Nevertheless, just try to revise a bit. What happens usually is we are having a NPN transistor here as well, but then this is a channel that we have. This is the N channel, and these two are called the P channel. So you know this is an NP junction and this is a NP junction. Okay, so we have got two NP junctions here. On this side we have got a gate. Okay, and on this end we actually are having a drain, and this end we have a source, right? And depending on the biasing we can actually have the width of this changing. So if the width changes, the electron will have actually lesser space to move, as a result of which the movement of the electron will be restricted. Okay, so why does that happen? Because this side is reverse biased, and on this end also it's reverse biased. So if it is reverse biased, we do understand that the width of the depletion region will increase, and if the width of the depletion region increases, what happens is that the electron will have lesser space to move around. Okay, as a result of which this flow of electron will be more or less channelized. Okay, so this is something which we have seen superficially the other day. We are just going to note down some points today which are important. Okay, so I think this is something which we already did. So first is we actually got two types of channels here. So one is the N channel, okay, and the second one is the P channel. Okay, now you need to understand one thing, that in exam if I'm asking you for P channel, you just need to look into it in a different way. N channel means whatever is the in between one. Okay, so it is N here, so we call it as N channel. If it is P, we'll call it as P channel, but then these will be N and this will be N. Okay, so this is something which we should start with. Okay, so in general, if we just write down a few points here, okay, which we have already seen, there are two junctions. Okay, there are two PN junctions. Okay, so that is important. Okay, and one more thing is when the width, this is actually the working. Okay, so you need to understand that how exactly it works. I've already told you verbally, but I'll just give you some sentences which are important. Okay, when the width of depletion region, okay, is increased, the electrons motion in the N region is obstructed. Okay, so I think this is quite simple. When the width of the depletion region is increased, the electrons motion in the N region is obstructed. So this is the depletion region that we have. So in general, if you consider any kind of PN junction, we definitely have a depletion region, and we know that if we are actually putting it in reverse bias, okay, we are basically going to have a depletion region, okay, which will increase with the applied voltage. So the working principle more or less remains the same as that of a junction diode, but then you have to understand that we have got a gate, drain and source in construction, which is kind of different. Okay, so this width that we are talking about, the width can be, so when you write it on your exam during for construction and the working, you can actually consider these points. Okay, width can be controlled via the gate terminal. Okay, so you know this gate terminal that we are talking about is very important. Okay, because of this the width will more or less be adjusted. Okay, so the width of the can be controlled via the gate terminal. Okay, so that's important. So what happens is you can just probably write down 2 points here. Hence the voltage, okay, and we are talking about the gate source voltage here. Okay, and we will write it down as VGS. Okay, will be controlled by the IB. Okay, so you know this drain current that we are talking about, that will actually control the gate source voltage. Okay, so maybe I can just write it down here. Okay. So this is the gate source voltage, and this will actually depend on what is the drain current that we have. Okay, so that is also a dependent factor here. Okay, so that is important. So not will be controlled, sorry, this is will control ID. Okay. So it will basically control ID. So the current is actually controlled by the gate source voltage. So if that happens, we can actually call it to be the voltage controlled device. Okay. So what happens is, that is why it is actually called a voltage controlled device. Okay. Hence, it's a voltage controlled device. Okay, so it's a voltage controlled device. Okay, now how do I really understand this? We can actually take an analogy. Okay, please don't concentrate on this analogy too much during your exam, because sometimes I've seen that you'll just concentrate on this because this is something which you understand. But when you write down these points, you have to understand the physics and write it down properly. Okay, so the analogy might be water flowing from a tap. Okay, so you basically have a tap and water flows, and there you can actually consider the condition under which the working will be similar to a JFET. Okay, a junction field effect transistor. Okay, so first thing is cause of water flow. So cause of water flow, so when you basically consider a tap water, you basically, let's say you have a tap here. Okay, you have a tap here, and then let's say you have a tank here, water tank. Okay. And what happens is, you are basically going to connect a tap. Okay, not very good at drawing, so I can understand this. You're connecting it to the water tap. Okay, and this is actually at a height h. So in general, we say that this height h is nothing but the potential. So higher the tank is, more would be the potential. So that means the water that flows through the tap, as soon as you on it, okay, you are going to get it because of the difference in potential. So here also, if you're talking about the current, that also flows because of the change in potential. So cause of water flow, okay, which can be actually analogous to the cause of electron flow. Cause of electron flow. Okay, so I hope you understand this, because this is nothing but happening because of the difference in potential. Okay, then we have got valve knob of tap. Okay, we have got the valve knob of tap. Okay, and here that means you are using this valve knob to switch it on. Okay, so what happens is, you are using this knob, you are switching it on, and then the water flows. Here also you can actually have the valve knob comparable to the gate of JFET. Gate of JFET. Okay, we have got the gate of JFET. That can be actually a good analogy. Okay, next we have got the sink in tap water. Okay, you mean tap water, but in general we have it here as the drain. So we basically have got the drain. Okay, so we've got the sink and we have got the drain. So drain is in JFET and sink is in the tap that we're talking about. Okay, and then finally we have got the tap. Okay, and here we are basically going to call it as the source. Just look into it this now. We have got the source. We have got the source. The electrons are flowing from this end to the other end. So that means this is where the electrons are getting dumped, okay, or going towards this direction. So this is the drain. The electron starts from here. So this is the source, okay. And if you're considering the gate, that means you are going to apply a potential across this. Okay, based on this you are going to get the current, right? So that means that is nothing but acting as a knob of the tap. Okay, And why does the water flow? Because we have got a potential. Okay, so I think this is a good analogy to understand this factor. Okay. Okay, next we are going to look into something which is very interesting. The point here is that this depletion region that we have here basically will keep on reducing in size as we go from up to down. So it will be thicker here, the depletion region, and as we go towards the bottom, the depletion region will become thinner. The question is why? Okay? Why it becomes thinner, and this is something which we're going to look into now. Okay, so what I will do probably is I'll just copy this and put it into the next slide. Okay, so I'll put it into the next slide, it'll be more easy. Our target is to find the value of x and y. Okay. So let me just give some potential now. Okay, so what I'm going to do now is I'm going to apply some potential. So we have this here, okay, and we have it here. Okay, and what is the potential here? We are just going to write it down. Okay, so the gate source voltage is maintained at a potential V. Sorry, take the pen. The gate source voltage is maintained at a potential of VGS is equal to 0. So that means we are just short circuiting it. Okay, we're directly connecting it. The potential here and the potential here are the same. So what we can say is that the gate source voltage, the potential is more or less 0. Okay, and that's the input. Okay, on the output, what we are going to do is we are going to connect this. Okay, take this. Okay, I'm going to connect it with the source. Okay, so I will take this, take a bit gap here. Our system of linear equation is written F1 B. Okay, so we have this, and now what we can do is we can actually connect this. So I'm talking about a reverse bias here. So you see this is basically a reverse bias connection. Okay, this is a reverse bias connection. Okay, so you see this is N, this is P. Okay, and you can see that the source is connected here. Okay, via the gate. Okay, so you can consider this to be a kind of reverse bias connection. Okay, and from here we are going to understand this, what exactly happens here. Okay, before that, maybe I can just give you a small note on ID. Okay, so maybe I can write it down somewhere. This ID is basically nothing but the conventional current. Conventional current. Okay. So you might be a bit confused, like what is the direction of current that we are considering. So I hope all of you know there is a difference between the electronic current or the conduction current and the conventional current. So the conventional current will flow in this direction, the electrons will flow in this direction. Okay, so current will always flow in a direction opposite to the flow of electron. I think this is something which you have studied in the lower classes. Okay, so this is opposite to flow of electrons. So please note this before we actually go into the next part. Okay, so what happens is, if you are considering this particular connection, okay, so we'll just take the case here. Okay, let's consider the case. The case is VGS is equal to 0. Okay, VGS is equal to 0 and VDS is actually greater than 0 volt. So this part, which is actually VDS, the drain source voltage is actually kept at a voltage greater than 0. Okay, and the gate source voltage is kept at 0 volt. Okay, so that means this side you are actually applying some potential. Okay, and then we are going to just look into this case. Okay, so what happens is, in this particular condition that we are considering here. Okay, in this condition, and so what happens is, in this condition, the width, okay, the width of the depletion region is going to vary. Okay, the width of the depletion region, okay, will be more at the, okay, so will be more at the top. Okay, and less at the bottom. So what we are going to do now is we are going to analyze that why this is the case, that the width will get more at the top and less at the bottom. Okay, so this is important. Okay, let's try to understand this. So here what happens is this N channel, okay, what you need to notice is this N channel behaves like a resistor. Okay, let's check this out. Okay, so let's try to understand this from probably a diagram that we're going to draw. Okay, so let's draw four resistors here. Okay, let me say one. I will take one more here, one more here. Okay, okay, and then might be at one at the bottom. So let me just draw some resistors here. Okay, then okay, so maybe I can use the pen directly if I'm lazy. Minus 2b, okay, 2b and plus 2 is operating on here. So of course it doesn't look like the same, but then all the resistors of equal values. Okay, so I'm just putting some equal values for the resistor. Okay, so we have got these resistors here. Okay, and maybe I can just write down the values here. So all these are actually resistance R. This is R, this is R, this is R, and this is also R. Okay, and let's say I'm going to apply a potential across the two ends. So we will apply a potential across this end and across this end. Okay, and if we just look into the potential, let's say I am applying a potential of 2 volts. Okay, so let me say I'm applying a potential of 2 volts. So the voltage is 2 volts. Okay. So if you are actually going to measure the potential across any of these, okay, you are going to look into a drop. Now since all these resistors are equal, you are going to have a drop of 0.5 volt. Okay, drop. Let's say this is 0.5 volt drop. Okay, and you are going to have the same drop across this is also will be 0.5 volt drop. This will also have a 0.5 volt drop because these resistors are connected in series. Okay, and the potential drop will be equal because all these resistors are of equal value. Okay, so if you actually use a voltmeter and try to measure the resistance across this end and this end, you are going to get 2 volts. Okay, but then on the other hand, if you are going to measure a resistance between these 2 points, okay, let's say this point and this particular point, you are going to get the voltage to be 1.5 volt. So what happens usually here is that the resistance is more or less going to change. Okay, so if you go to the lowest end, let's say across these two ends, okay, maybe I can just extend this. Okay, if I take across this end, I am going to have only 0.5 volt. Okay, now since this is connected in reverse bias condition, okay, we are going to have a voltage drop. Okay, so this particular region is going to act like a set of resistors. Okay, connected in series because electrons are flowing and we have got this depletion region, so electron will actually get a path of resistance that is being offered. Okay, so this n channel will basically behave like a resistor. Okay, so maybe I can just write down some sentence here. Okay, so on the upper portion, okay, on the upper portion, on the upper portion, okay, we have the potential difference. The potential difference, okay, is 1.5 volt. Okay, between gate and drain. Okay, between gate and drain, that's the value. Okay, terminal. Okay, so that means the potential is more at the upper part if we just try to relate it with this particular point. Okay, so up to this point maybe it's 2 volt, and then as soon as it comes at this particular point the potential becomes 1.5 volt. If we come at somewhere here, okay, if we come at somewhere here, the value might be around 0.5 volt. So since the potential is less, the depletion region will be thinner. Okay, the potential is more, the depletion region is going to be more. Okay, so the width is more. And if you consider the lower portion, potential is 0.5 volt. Okay, hence the, so this is important, you please try to explain it in proper words. Okay, I'm just writing it in short. Hence the width of the depletion region is less. Okay, so this is very important. So that is why that the potential width, okay, the width of this potential will actually keep on varying. Okay, so this was something which was important in this gate part. Okay, so the next thing that we are going to do is the output characteristics. Okay, so output characteristics is something which is similar, but then it is being controlled by a different factor, because previously when we looked into the output characteristics, we were looking into the system which was actually a current control device. Now we are basically going to have a voltage control device. Okay, so we're just going to look into the output characteristics of this particular device. Okay, so let me just take a new page. Okay, and I'm just going to write down the figures here. Probably tomorrow we are going to look into it in more detail. Okay, output characteristics of JFET. Okay, so I'm just going to look into the output characteristics of JFET. So see, every time I'm doing this, I'm trying to draw the diagram, and when you draw the diagram, you're actually having a good practice. So all of you should actually practice it once or twice. Okay, okay, characteristics. Okay, so output characteristics. So let's just draw the diagram for a JFET now. I think we have already done it for a normal junction, bipolar junction transistor. I'm just going to look into it at JFET now. Okay, so just concentrate on this, and probably this is the diagram that we're going to use next. Okay, so what I'm going to do is I'm going to apply a biasing at the input. Okay, and then I'm going to apply the biasing via a resistor. Okay, so putting a resistor is important. As you look into the diagram, this should be clear. Okay, so okay, we're just going to have a resistor here. Okay, and then we are going to take the output across the resistor. Okay. We are going to have, let's say, the gate terminal here. Okay, and then we will have drain on one end. Please remember the symbols for the different transistors. In exam, if you're drawing the symbol wrong, your entire sum gets wrong. Okay, here also we are not going to apply anything at the bottom, so probably at the bottom the best way would be to start with drawing a straight line. Okay, we're just going to connect it. Okay, so we have this, and then probably we are going to measure the current at some point, the drain current. Okay, so I'll just leave that gap here. Okay, and then we are going to measure the output across the another resistor. Okay, so I just take another resistor here. So since I'm using a tool here, a software which actually helps me to draw a bit better, but then don't worry, during exam I would suggest don't sit with a scale and a pencil and keep drawing and wasting time. Okay, better to just draw it fast. It should be legible, it should be okay, and that should be fine. Okay, so maybe I can just draw the batteries here. Okay, so this is the linear differential equation with constant coefficient. Okay, so this is the input terminal. Okay, and then we can draw the output terminal. We just look into the biasing. Okay, I think biasing is something which is clear to you now. We've already studied about biasing in the last class. So please don't put up wrong biasing. That would be difficult for you to understand. Okay, so maybe I can just put one more here. So this is the battery that we have. Okay, and then probably we should actually draw the resistor. Okay, so maybe I can draw it here. Okay, this is the complementary function. What is the particular integral? And then this way might be, I can just put 1. 6 e to power 2 is divided by d square plus 4 minus 5. So you're just going to have the output across this, input across this, and output across this. Okay, so this is the basic structure. Okay, and then I think we already know about this. Okay, we do have gate terminal here, so I'll just put it here, and then I will put an arrow on this side, so that means I'm talking about a n channel gate. Okay, so please remember this, don't get confused. It's very important that you put the symbols correctly. Okay, and then we just measure the gate voltage, so we need to connect a voltmeter. Okay, so input and output. In input we measure the voltage, okay, and output we measure the current and the voltage, right? So maybe I can just connect voltmeter here also to measure another voltage. Okay, and then let's see what we can measure. So it's basically a voltage control device, so I will put a voltmeter. Okay, so I put a voltmeter. So what I do is I will measure the voltage, and that is nothing but the gate source voltage, right? This is the gate and this is the source. Okay, so if you're looking into in a mobile screen, it becomes a bit small, so you can always watch into it as full screen. Okay, just try to check that. And then you are just going to have the output voltage, and output voltage is across the drain and the source. Okay, just to make things clear, this is your gate. Okay, this is your drain and this is your source. So gs across this, and ds means ds across this. Okay, so you're going to measure the you're going to give an input voltage, and based on that you're going to get the output voltage and the output current. So you're going to connect an emitter here and you're going to measure the current. So this is drain circuit, so this is id. You can always level this as d, g and s. Okay, so I think this will be easy for you, all of you. Okay, so maybe keeping the conventions similar, I should write down s here. So let me just put s here. So that's the source. So this is the measurement that you are going to basically use. Okay, so please remember this circuit. This is something which is very simple, but also remember that this is not something which is similar to a BJT. Okay, bipolar junction transistor. Bipolar junction transistor, we do have a current source. Okay, we do have a current measuring system because we need to control the current also, based on which the output will work. But since it is only a voltage control device, we're just going to write down the voltage part here. Okay, so please look into these things carefully and check what is the difference between them. Okay, that's important. So how does the output characteristic curves look like? Okay, so it looks like something like this, something similar, but then you're not measuring the current based part, we're just going to measure the voltage here. So when you learn everything together, I think this will be more easy for you. Okay, so you are going to plot a graph between the output current id, okay, and then the voltage vds. Okay, so this is something you're going to measure. The behavior is going to be something similar. Okay, I'll just draw a few of the representative curves here, maybe two, maybe one more. Okay, so you see it basically starts going up at this particular point. Okay, so it basically starts going up at this particular point. Okay, so you have this region. Okay, OA, let's say. Okay, let me just write it down as some, let me just level this up. Okay, this is O, this is the origin or 0, and this is VP. I'll tell you what is VP here. Now when we looked into the output characteristics of a BJT, what we said was that this is actually dependent on IB. If we're considering a common emitter configuration, we say that this is actually dependent on the input, the base current. Okay, but here it's not the base current, it is going to be VGS. Okay, so we are going to have a VGS. So let me write it down here, VGS. Okay, so if you VGS is actually going to be more, you are going to get less current because it's in reverse bias. Okay, I think you understand this. Please don't mix up this part, this is important. VGS is, let's say, 2 volt. Okay, and this is VGS is equal to 1 volt. So since this is connected in reverse bias, if we have more gate source voltage, the depletion region is going to be more. As a result, the current is going to be less. Okay, so maybe I can write it down here. VGS is more. Okay, the depletion region DR, okay, is going to be more, and as a result of which this current that we are talking about, the drain current, is going to be less because this is going to pinch it off. Okay, and this VP that we are talking about, okay, is called the pinch off voltage. So I think I'll give you the definition tomorrow, but then I think it's clear from this that the pinch off voltage means the voltage at which the current is maximum. Okay, pinch off voltage. Okay, so pinch of voltage. So this is important. So this is actually the output characteristics, and this is something which you should know. So I'm not going to continue with the different terms, the terms and some important topic on this particular topic of output characteristic is something which we are going to discuss tomorrow. Okay, and we are also going to look into something which we call as output characteristics. Okay, so this is where we stop.